Hey folks, welcome to another set of Intro Chem video notes. In today's lesson, we're going to learn about interparticle forces. More specifically, we're going to learn about how these forces that hold particles together affect the properties of substances that you can see in the large scale. Let's get started. There are two types of interparticle forces, intramolecular and intermolecular. The prefix intra means within, and inter means between. So when we're talking about intramolecular forces, we're talking about the attractive forces within a molecule, those things that hold atoms together. You've already learned about these. They're just chemical bonds. As you know, there are three types of bonds: metallic, ionic, and covalent. All three of these are incredibly strong and take a lot of energy to break apart. You can think of them like really strong magnets. Intermolecular forces are the attractive forces between molecules. They're the reason that most molecular substances are soft or easily broken apart. They're on the order of about 400 times weaker than actual bonds, so they don't take a lot of energy to break apart. These are the forces that attract one molecule to another molecule. They don't actually bond the two molecules together, so instead of thinking of them like really strong magnets, maybe think of them as fairly cheap Velcro. The two molecules will stick together, but they're not terribly difficult to pull back apart from each other, because these intermolecular forces are way weaker than chemical bonds. Here's a nice illustration of hydrogen chloride. In a single molecule, one hydrogen atom and one chlorine atom are bonded together, in this case, sewn together. It takes a whole seam ripper and a lot of work to separate them. However, between one hydrogen chloride molecule and another hydrogen chloride molecule, there's some sticky Velcro. Several molecules might come and stick together, but when you pull them apart, the individual molecules stay intact. The difference between them being stuck together via that Velcro and pulled apart into individual molecules is the difference between whether that substance is currently in its solid or liquid state. Let's do a quick review of our intramolecular forces. First up is metallic bonding. As you've learned, the positive nuclei of metal atoms will arrange themselves in a fairly orderly fashion, and their valence electrons will flow freely as a sea of electrons between them. The attraction that holds all of this together is the attraction between the positive metal nuclei and their negative sea of electrons. This is a very strong attraction, so metallic solids have very high melting points. Also, the free-flowing electrons allow metals to conduct electricity. You'll know a substance has metallic bonding if all the atoms are metals. Ionic bonding occurs when a metal atom donates its valence electrons to a nonmetal atom. The metal becomes a positively charged cation, and the nonmetal becomes a negatively charged anion. In ionic substances, the force that holds everything together is the attraction between the cations and anions, because opposite charges attract. Covalent bonds are formed when two atoms share the same pair of electrons. In other words, both atoms grab on to those electrons and try to claim them for themselves in an eternal tug-of-war of sorts. The attraction is between the nucleus of each atom and that shared pair of electrons. When all the atoms in a substance are held onto each other with covalent bonds, we call this a covalent network solid. These are things like diamonds, graphites, or quartz. Substances that have covalent bonding may also be made up of distinct individual molecules that aren't chemically bonded together. These are called molecular substances or molecular solids. The attraction that holds these molecules together in their solid state is that relatively weak intermolecular forces that we were talking about. In those images here, those are represented with dotted lines. The main differences between molecular solids and metallic covalent network or ionic solids are that when you melt a molecular solid, it doesn't often take a lot of energy, and you still have the same individual molecules intact as you had before. When you melt a non-molecular substance, you end up with individual atoms, and it takes a whole lot of energy to do this, because we have to break actual chemical bonds. Before we talk about those intermolecular forces that hold molecules to each other, let's recall the two types of covalent bonds, polar and nonpolar. when the two atoms have a significant difference in electronegativity values, like greater than 0.4, one atom pulls that shared pair of electrons towards it more and causes itself to be slightly or partially negative. The other atom, the less electronegative one, feels those electrons less, so it becomes slightly positive. Having a positive and negative side of something makes it polar, like the two poles on a magnet or the two poles on Earth. Molecules with clearly distinct partially negative and partially positive sides are called polar molecules. These partial charges can lead to some new attractions that make polar bonds stronger than nonpolar bonds. Nonpolar bonds exist between two atoms that have the same or nearly the same electronegativities, a difference of less than 0.4. Both of them are pulling on those shared electrons with about the same strength, so neither of them pulls the electrons closer towards it, and that means neither of them feel partially negative or partially positive. So there's no polarity to these molecules. Since these don't have any additional charges, nonpolar bonds are slightly weaker than polar bonds. All right, folks, intermolecular forces. First up is dipole-dipole. A dipole is just another name for a polar molecule. Di means two, and pole is referring to the charged side of a molecule. So if it has two charged sides, positive and negative, it's a dipole. Dipole-dipole forces exist between two molecules that are polar. Like any other time we have positives and negatives together, this works because there's an attraction between opposite charges. The partially negative side of one molecule will be attracted to the partially positive side of another. The larger those charged sides are, the stronger this attraction will be. This is incredibly weaker than any actual type of bond, but it's a fairly strong type of intermolecular force. As such, polar molecules tend to form solids with higher melting points than nonpolar molecules do. A special type of dipole-dipole attraction exists and is known as hydrogen bonding. It's a little confusing because it's not actually a bond. That's just what we call it. It's much stronger than any other dipole-dipole attraction. As we said, the more polar the molecule is, the stronger the attraction. So when we get the hydrogen atom with its really low electronegativity covalently bonded to one of the three atoms that have the most electronegativity on the periodic table, fluorine, oxygen, or nitrogen, we end up with incredibly polar molecules that exhibit these three strongest types of dipole-dipole attractions. So you'd look for an H covalently bonded to F, O, or N. Then you'd recognize that the H will have a really large partial positive charge, while the F, O, or N have a really large partial negative charge. The attraction between those positives and negatives from one molecule to another are the hydrogen bonding attractions that we're talking about. These are the strongest of the three intermolecular forces, but still way weaker than any actual bonds or intramolecular forces. This is why water, H2O, has a boiling point that's way higher than H2S or H2SE. They all have the same shape and same kind of polarity, but the large electronegativity difference between H and O puts H2O in its own class of attractive forces. Lastly, London dispersion forces, or LDFs for short, are the weakest type of intermolecular force. They exist between every particle, molecule, or atom that have electrons, which is all of them. In the previous two examples, electrons were permanently stuck to one side of the molecule in a lopsided or unequal manner, creating permanent partial charges. For LDFs, partial charges are caused by those electrons moving around randomly and occasionally ending up lopsided or unequal and creating those temporary partial charges. These are small and temporary charges, so these forces are much weaker than dipole-dipole forces with their permanent charges. LDFs can largely be ignored when polar molecules are involved because they're usually fairly weak in comparison to dipole-dipole forces. However, the more electrons a molecule has, the more LDFs it has. So sometimes LDFs can play a major role in determining the properties of substances. For nonpolar substances, it's the only force we're going to look at. For instance, this is why Cl2 with only 34 electrons is a gas at room temperature. It doesn't stick together very well. But Br2 with 70 electrons is a liquid, and I2 with 106 electrons is a solid. That's all to do with the LDFs because these are similar nonpolar molecules. So, how does this relate to the properties of a substance? Easy peasy. The more attraction, the more energy it takes to pull molecules or atoms away from each other. When there's more attraction between the particles, the substances will have higher melting points, higher boiling points, a higher surface tension if it's a liquid, and a lower vapor pressure, which means fewer particles will escape the liquid phase and convert to the gas phase. Some substances are able to conduct electricity, most are not. Any metallic substance will conduct electricity due to the free-flowing sea of electrons involved in metallic bonding. In order to conduct electricity, you have to have charged particles that are able to move. So ionic substances have charged particles, but as a solid, those particles cannot move. So ionic solids cannot conduct electricity. If you melt the solid into a liquid or dissolve it into solution, then the ions are now free to move, and they can carry electricity. Lastly, covalent substances, whether network or molecular, never really have fully charged particles, so they don't conduct electricity in any situation. Here's a quick summary of the types of properties you can expect from each of these types of substances. Metallic, ionic, and covalent network substances all have very high melting and boiling points, as all of the particles are held together by strong intramolecular bonds. Molecular substances are only held together by relatively weak intermolecular forces, so they have relatively low melting and boiling points. Metallic substances are strong, ductile, and malleable as well. Ionic substances form solid crystals and are hard and brittle as solids. Covalent network solids are generally very strong, and molecular substances are usually soft and easily broken apart, but can have a large variety of different properties. So if you're given two substances and asked to compare based on their properties, here's what you do. First, figure out what holds all the particles together for each substance. If one is a non-molecular substance, such as metallic, ionic, or covalent network, and the other is a molecular substance, the first one has a much higher boiling point. If they're both held together with ionic bonds, you look for the charges of the ions. Something with a 2 plus and 2 negative versus 1 plus and 1 negative will have stronger attractive forces. So whichever has larger ionic charges has a higher melting point. If they're both molecular, you have to dig a little bit deeper and determine the intermolecular forces present. First, look for any hydrogens directly bonded to F, O, or N. If you see that, then you know the molecule has hydrogen bonding. If only one of them has hydrogen bonding, it's the one with a higher melting point. If they both do, look for how many different H's attached to F, O, or N you can find. The more hydrogen bonding sites a molecule has, the more attraction there will be. If neither molecule has hydrogen bonding, look for whether or not the molecule is polar. A molecule is polar if it has polar bonds and they don't cancel each other out. Essentially, one side of the molecule has all the partial negatives and the other side has all partial positives. So if one is polar and the other is not, the polar one has more attraction with its dipole-dipole forces. If they're both polar, whichever one is more polar is the one with a higher melting point. Lastly, if they're both nonpolar, you only have to look at the London dispersion forces because that's all they have. The larger molecule with more total electrons will have a larger electron cloud and will therefore be more polarizable or have stronger LDFs. Of course, the best way to know for sure would be to actually melt these substances in a lab and find their melting points. Alright, this is the very last thing for this set of notes. At this point, you've made it quite a ways into the notes, so feel free to take a really short brain break and draw a cutesy Santa Claus or North Pole related scene in the bottom left corner of the page you're currently working on in your notebook. This will get you some extra credit points. Alright, How do we tell if a molecule is polar? That's a great question. First, you have to see if you have polar bonds, and if so, see how polar those bonds are. We measure polarity by finding the difference in electronegativity between the two atoms of a bond. So subtract the two electronegativity numbers for those two atoms, and the larger that difference is, the more polar that bond is. When we have a molecule drawn out in its three-dimensional shape, we can assign dipole moments to each bond. These are just arrows that point from the less electronegative atom to the more electronegative atom. And these arrows show the general amount of forces the electrons are being pulled by and in which direction they're being pulled. Do this for each bond in the molecule. If you have dipole moments like this molecule that point in opposite directions, they cancel each other out and you have a nonpolar molecule. There's a glue-in for your notebook that gives you a list of symmetrical shapes in which the dipoles will cancel out if all of the outer atoms in the molecule are the same element. If the shape of the molecule is not one of those handful of symmetrical shapes and they have polar bonds, then it's a polar molecule. Basically, if you draw the partial negative and partial positive charges on the atoms correctly, more electronegative atoms get partially negative charges, less electronegative atoms get partially positive charges, and you see that there's clearly one side of the molecule with all the negatives and the other side with all the positives. That's a polar molecule. Well, that's all for today, folks. Thanks for bearing with me. As always, if you have any questions, just ask.